Hello, and welcome to my video series on algorithms. This is part 2 of Module 6, Dynamic Programming. In this video, we will present the weighted interval scheduling problem. Imagine that you are managing a computer server that can execute only one job at a time. The ith job, denoted as Ji, requires ei units of time to complete and must be finished by a deadline fi. If you can successfully complete the job, it will yield a profit of Wi. Given a set of jobs with this information, your task is to find a subset of jobs to run such that the total profit is maximized. Keep in mind that we cannot schedule all jobs due to the potential conflicts between them. For the job Ji, we know that it needs ei time to run and must be finished by its deadline fi. From this, we can easily infer that the job must start at Si equals Fi minus Ei. In other words, job Ji will occupy the server during the time interval from Si to Fi, preventing any other jobs from running during that period. For example, as shown in the figure, jobs Ji and Jj conflict because their execution intervals overlap. Similarly, jobs Jj and Jk also conflict. However, jobs Ji and Jk do not conflict and can both be included in the same schedule. Therefore, we cannot simply execute all jobs. Instead, we need to find a subset that maximizes the total profit. Formally speaking, we are given a set of jobs J where the ith job needs to start running at Si and finish at Fi. If completed, the job will yield a profit of Wi. The weighted interval scheduling problem involves finding the subset J prime such that no conflicts exist in J prime, and the total profit of jobs in J prime is maximized. Here, by weighted, we mean each job is weighted by its corresponding profit Wi. And by conflict, we mean the execution time intervals of two jobs overlap. In the unweighted version of this problem, where all jobs yield the same profit, a greedy algorithm can provide an effective solution. The greedy algorithm progressively schedules the job that ends the earliest. The intuition behind this is to maximize the remaining time for other jobs to run. Now, for the weighted version of this problem, we shall also explore whether a greedy algorithm could work. We proposed three potential greedy criteria. The first criterion mirrors the solution to the unweighted interval scheduling problem, where we prioritize the job that has the earliest finishing time. The second criterion prioritizes the most profitable job. The third criterion prioritizes the job that has the highest profit rate, which is defined as the profit Wi divided by the execution time Ei. Consider the instance shown in the figure. When applying the earliest finish time first criterion, we will schedule Ji because it has the earliest finish time. Scheduling Ji prevents us from scheduling Jj due to the conflict between them. Subsequently, we schedule Jk because it does not conflict with Ji. The resulting total profit is $900, which is smaller than the actual maximum profit of $5,000, which is achieved by scheduling Jj alone. Second, if we use the highest profit first criterion, we would schedule Jj, leading to a total profit of $1,000. However, we know that the actual maximum profit for this instance should be $1,600, which is achieved by scheduling both Ji and Jk. Third, consider the highest profit rate first criterion. Job JJ will be selected because it has the highest profit rate, given its highest profit and shortest execution time. Scheduling JJ will result in a total profit of $1,000, which misses the actual maximum profit of $1,600 that is achieved when scheduling both JI and JK. As a result, it is not easy to find a simple criterion that can lead to a correct greedy algorithm for this problem. Therefore, we will explore a solution using dynamic programming. Let's begin with defining the subproblems. Intuitively, we can define subproblems using specific time points, where later time points represent larger problems and earlier time points correspond to smaller problems. In other words, given a time point t, we define MT as the maximum profit that can be obtained up to that time point. Keep in mind that we are working with a finite time frame here, which is bounded by the earliest start time and the latest finish time among all jobs. Although the time frame is finite, it can still contain infinite number of time points t, leading to an infinite number of subproblems. To address this issue, we observe that no profit is made if a job is not fully executed. For instance, in the figure, job JK is still running at time points T1 and T2, but finished only at T3. Thus, considering subproblems MT1 and MT2 is unnecessary, because JK cannot be finished at those time points and will not contribute to the total profit. The only relevant subproblem is MT3, which corresponds to the finish time of the job JK. In other words, we define subproblems only for time points that correspond to the finish time of some jobs. This approach reduces the number of subproblems to the number of jobs, which is finite. It will further allow us to simplify the notation MFI as MI, where MI represents the maximum profit we can get up to the finish time of the job JI. To determine whether such a subproblem definition allows for a dynamic programming solution, we need to verify the two key requirements of DP. They are the existence of overlapping subproblems and an optimal substructure. First, let's examine the existence of overlapping subproblems. Consider the three jobs JI, JJ, JK, along with their associated subproblems MI, MJ, and MK. Observe that there is no conflict between jobs JI and JJ. The maximum profit MJ can be computed by adding the profit of JJ to the previous maximum profit MI. In other words, MJ equals MI plus WJ. Similarly, since there is no conflict between jobs JI and JK, we can compute MK as MI plus WK. Therefore, the solution to the subproblem MI is used for computing the solutions for both MJ and MK, making MI an overlapping subproblem. Next, we will verify the optimal substructure. From our previous analysis, we know MJ equals MI plus WJ. Since the profit WJ is specified by the input and therefore a constant, MJ can be maximized if MI is maximized. Therefore, the subproblem definition indeed has the optimal substructure. After verifying the problem is solvable using DP, we can proceed to design the algorithm. Remember that designing a DP algorithm typically involves 3 steps: partial ordering the subproblems, writing the top-down recursion, and performing the bottom-up tabulation. First, let's establish a partial ordering among the subproblems, which means specifying the dependency among them. From our prior analysis, we know that subproblems defined at later time points depend on subproblems defined at earlier time points. Since subproblems are defined based on the finish time of the jobs, we can order the subproblems by sorting the jobs according to their finish times. If there exist ties, we can break them arbitrarily. This is because two jobs that have the same finishing time must conflict with each other, meaning they cannot both be scheduled. As a result, their solutions do not depend on each other, and the way we break the tie does not affect the overall solution. Next, let's write a top-down recursion, which should describe how a larger subproblem is solved using smaller subproblems. For the instance shown in the figure, we shall describe how to compute the largest subproblem, Mk. We begin by discussing the case where the job Jk is scheduled. Since Jk is scheduled, Mk should not depend on Mj because the jobs Jk and Jj are in conflict. Therefore, Mk should only depend on Mi1 or Mi2. Since the job Jk has no conflict with either Ji1 or Ji2, it can depend on both subproblems. Thus, Mk should be the larger of Mi1 plus Wk and Mi2 plus Wk. However, since Mi2 corresponds to a later time point than Mi1, Mi2 will always be greater than or equal to Mi1. This means that Mi2 cannot lead to a lower profit when given more time to schedule jobs. As a result, Mi2 plus Wk is guaranteed to be larger than Mi1 plus Wk. Therefore, we can simplify the dependency of Mk to rely only on Mi2 and express Mk as Mi2 plus Wk. So, how should we characterize the job Ji2 in a more general way? First, because job Jk is scheduled, Ji2 must have no conflict with Jk. In other words, Ji2 must finish before Sk, the start time of Jk. Additionally, Ji2 must have the latest finish time among all jobs that finish before Sk to ensure the maximization of Mk. Together, we can generalize Ji2 as the job that has the latest finish time among all jobs that finish before Sk, and we denote this job Pk. In other words, if the job Jk is scheduled, the corresponding solution depends on Pk. Thus, we can compute Mk as Mpk plus Wk, assuming that the job Jk is scheduled. Now that we have considered the scenario where Jk is scheduled, let's discuss what happens if it is not scheduled. If Jk is not scheduled, we won't gain any profit from it. However, it will not conflict with any job in the current schedule either. In this case, the maximum profit remains the same as the previous maximum achieved before considering Jk. By definition, this would be Mjk-1. Therefore, we can compute Mk as Mk-1 when assuming Jk is not scheduled. Clearly, Jk is either scheduled or not scheduled. The optimal plan should correspond to the option that yields the highest total profit. Hence, Mk is simply the maximum of Mpk plus Wk and Mk minus 1. The third step is to perform bottom-up tabulation to compute the final result. Given the recursion function, we observe that the subproblem M is characterized by a single parameter, the job ID. Therefore, it is sufficient to use a one-dimensional array as the DP table to store the intermediate results of the subproblems. Intuitively, the ith entry of the DP table will store Mi. Computing Mk depends on Mpk and Mk-1, both of which correspond to entries to the left of Mk. As a result, we can simply fill the DP table from left to right, ensuring that the solutions to all dependent subproblems are available when needed. For the boundary case, we need to specify how to compute the first few entries in the DP table, as their dependent subproblems may be undefined. For instance, consider the first subproblem M1, which corresponds to the job with the earliest finish time among all jobs. The subproblem M0 is associated with a non-existent job that would end before F1, the finish time of the first job J1. Similarly, the subproblem MP1 will be associated with a non-existent job that ends before S1, the start time of J1. To handle both undefined cases, we introduce a dummy job that ends before both S1 and F1, or simply before S1. Besides M1, all subproblems need to have their dependent subproblems well defined. Hence, to satisfy the needs of all subproblems, we create a dummy job that finishes before the earliest start time among all jobs. Specifically, let the dummy job be J0, which finishes before the earliest start time among all jobs. It is important to know that the dummy job is created only to facilitate the tabulation process and has no real meaning. Since the dummy job does not actually exist, it does not generate any profit. Therefore, the maximum profit we can obtain by the finish time of the dummy job J0, or M0, is 0. For any job Ji, if there exists real jobs that finish before its start time, Pi will refer to a real job. However, if no such job exists, Pi will refer to the dummy job J0. In either case, the recursion for computing Mi will be well defined, ensuring that the tabulation process can be completed. We can summarize the bottom-up tabulation process with the pseudocode presented here. Line 3 sorts all jobs based on their finish times, which takes O n log n time, where n is the number of jobs. Lines 4 to 6 populate the DP table from left to right, according to the top-down recursion function, which involves O n iterations. Finally, line 7 returns the last entry of the DP table as the maximum profit we can achieve. Two issues remain unaddressed by the previous pseudocode. First, we did not specify how to compute Pi for each job Ji. Second, while the current algorithm finds the maximum profit, it does not identify which jobs should be scheduled to achieve that maximum profit. Let's first address how to find Pi, which corresponds to the job with the latest finish time before Si. A straightforward approach would be to compare the finish time of all jobs with the start time Si to find Pi. However, since the comparison will need to be done for each job, the overall time complexity would be O(n) squared. A more efficient solution leverages the fact that the jobs are already sorted by their finish time. The sorted finish time allows us to perform a binary search of Si to find Pi. Recall that a binary search only requires O log n time. Hence, this approach will reduce the overall time complexity from On squared to On log n, which is the same as the time required for sorting the jobs. Here is the revised pseudocode, now including the computation of Pi, which is highlighted in yellow at line 5. This version of the algorithm runs in On log n time. Lastly, let's discuss how to obtain the actual job schedule that maximizes the total profit. Remember that the decision to schedule a job is implied in the recursive function. Specifically, if mpk plus wk has a larger value than mk minus 1, then the job jk should be scheduled. Otherwise, jk should not be scheduled. This decision should have already been made when filling the DP table. So we just need to store this information for later retrieval. To achieve this, we will introduce another array T, which has the same dimension as the DP table. Specifically, if mk equals mpk plus wk, we will record yes in the entry tk, suggesting that the job jk is scheduled. Otherwise, we will record no in tk. Now, we need to post-process the information stored in the table T to find out which jobs to execute. It is important to know that we cannot simply schedule all jobs that have yes in the corresponding entries. This is because each entry Ti only stores the optimal schedule for the subproblem Mi, which may not correspond to the overall optimal solution Mn. For example, the second entry Tj stores the optimal schedule for Mj, which tells the maximum profit up to the finish time of the job Jj. In this case, Mj is $1,000 and can be achieved by scheduling Jj, indicating that the entry Tj should be marked yes. However, scheduling Jj does not align with the overall optimal solution of $1,600, which is achieved by scheduling Ji and Jk, but not Jj. As shown in this instance, we cannot simply schedule all jobs that are marked yes. We still need to carefully retrieve the subset of jobs that contribute to the overall optimal solution. Recall that the overall optimal solution is stored in the last entry Mn. According to the optimal substructure, the optimal schedule for the subproblem that contribute to Mn must be part of the overall optimal schedule. The reasoning can be extended recursively from the rightmost entries in T to the leftmost entries, which correspond to the base cases of the recursion. Because we check the table T from right to left, this technique is called traceback. Specifically, we start by recognizing that the overall optimal solution is stored in the last entry Mk. By checking Tk, we find a yes, indicating that we should schedule Jk. If we schedule Jk, the subproblem that were used to construct Mk must be Mpk. We then check the entry Tpk, which is Ti in this case. Again, we find a yes, meaning that Ji should also be scheduled as a part of the overall optimal solution. Finally, when we reach the dummy job J0, we can terminate the traceback process as it indicates the end of real jobs in the schedule. Here is the pseudocode summarizing the traceback process. In lines 4 to 7, we iteratively infer the previous subproblem and select the jobs to execute based on the information stored in the table T. Specifically, Line 5 handles the case where the corresponding job Ji is scheduled, and line 6 handles the case where it is not scheduled. Finally, at line 9, the function returns the subset of jobs to execute. Since the traceback procedure visits each entry in T at most once, it has a time complexity of O(n). With the addition of the traceback procedure, we now have the complete pseudocode for solving the weighted interval scheduling problem. In line 7, we record the information regarding which jobs to execute in the traceback table T. In line 9, we parse the information stored in T to recover the optimal schedule that maximizes the overall profit. The time complexity of the complete algorithm remains in O(n) log n. The space complexity is O(n), which is due to the allocation of the DP table M and the traceback table T. In summary, we have discussed the weighted interval scheduling problem and provide a dynamic programming solution. This solution has a time complexity of O(n) log n and a space complexity of O(n). Thank you for watching and see you next time.